Pairs of chiral molecules have the same physical and chemical property unless they interact with another chiral object. Because our body is full of chiral molecules, it has huge impact on biological activities. This chiral sensitivity distinguishes from a nasal decongestant from a powerful psychoactive street drugs. Most commonly used technique that can discriminate chiral molecules lack sensitivity, preventing their use to study chirality in dilute media, such as gas phase molecule.
One solution to this issue is photoelectron circular dichroism, also known as PECD. In a PECD experiment, we send a jet of randomly oriented chiral molecules in a vacuum chamber where it can interact with circularly polarized ionizing radiation. The photoelectron angular distribution is recorded by a velocity map imaging spectrometer. When chiral molecules are ionized by circular light, more electrons can be emitted in the forward direction than backwards. This asymmetry is a pure electric dipole effect and is extremely strong. It can reach several tens of %. This is what our VMI spectrometer looks like. Recently, we showed that tabletop circularly polarized XUV photons from resonant harmonic generation could be used to record PECD. We also investigate the influence of resonant enhancement in multiphoton ionization, showing that it is not necessary to observe PECD. At higher laser intensity, we reach the above threshold ionization regime, where we have measured PECD even for electrons ionized well above the ionization threshold. Last, we want to push the study to the tunneling regime. We use a strong 1.8 micron laser field to photoionize the functional molecules. Remarkably, even in this extreme ionization regime, we still measured a significant PECD. We can thus conclude that PECD is a universal effect in the photoionization of chiral molecules. This universality raises important questions. What is the physical origin of PECD? Is the process similar in single photon and tunnel ionization? To answer this question, the most natural option seems to solve the time-dependent Schrödinger equation for molecules interacting with a laser pulse and monitor the evolution of the electronic density, which is the square modulus of the electronic wave function. One can notice that because of the scattering of the outgoing electron onto the nuclei, the angular distribution of the freed electron gets structured. We can understand PECD as emerging from the scattering of the outgoing electron wave function on the chiral potential. More precisely, PECD was found to be due to the scattering phases of the electrons. This interpretation is certainly valid, but scattering phases may not be the most intuitive quantity to think of. We thus wonder if there was a classical interpretation of the origin of PECD. We solve the classical equation of motion of an electron in a circularly polarized laser field and a chiral molecular potential. The freed electron does not directly escape the molecule when it is ionized. It scatters several times on the molecular potential. The physical origin of PECD can thus be classically understood in terms of scattering of the electron trajectories in the chiral potential, which is close to the quantum pictures. This is true for any laser wavelength and explains the universality of PECD. If you want to know more, you can read our paper in New Journal of Physics Fast Track Communications. Enjoy!